the slide? Okay,
Yes.
great, perfect. So this is the toolbox we have been developing for disentangling string events. It's the AIDE Toolbox. It's a part of a toolbox was developed as part of the XAIDA project, and it was developed by a small, medium-sized team of people involved in this project. Maria, Jordi, Tristan, Monchue, Oscar, Gustavo, and me. The AIDE Toolbox is artificial intelligence for disentangling string events. And today what we are going to do is to show the toolbox capabilities, to show a description of the toolbox. My plan is also to show you a short tutorial with a simple use case so you can see how the toolbox works. These are the contents. I'm going to go to the next slide. These are the contents of the presentations. First of all, I'm going to do an introduction to what is string event monitoring and understanding some concepts which are important in order to follow the purposes of the toolbox, and also the AIDE Toolbox pipeline, a first introduction. Then we'll describe all the AIDE Toolbox stages, the user-defined modules, model training and validation, evaluation metrics and visualization of results, and the characterization and explainable AI modules we have integrated also for the analysis of streams. Then the tutorial. It's a track monitoring use case. We are going to see the data and experimental design, the model implementation, and also the model evaluation and intercomparison. And in order to finish, some take-home messages and the references. First of all, let me introduce these concepts about the string event monitoring and understanding. The purpose we have with this toolbox is to help users, or to try to bridge the gap between earth scientists and the machine learning community in order to make progress on string event monitoring, on string event detection and impact assessment. When we talk about the string event detection, it's about highlighting those spatiotemporal locations at which a particular stream, imagine a heat wave or a flood, is happening. These spatiotemporal locations, space locations through time. So the idea, or what the toolbox is going to provide as its output, is a series, time series of stream maps, of spatial stream maps. And these stream maps will allow us to discover underlying patterns and correlations between features at the moment the streams are happening. If instead of highlighting those spatiotemporal locations where the streams are happening, we would like to anticipate future streams, we would like to see if a stream will happen in the future or not, we are talking about forecasting. Forecasting is not covered by the toolbox, but I wanted to show this concept here in order to make the difference between detection and forecasting. Detection is covered, forecasting is still not implemented. Then the toolbox is also capable of performing impact assessment tasks. When we talk about impact assessment, the objective is to predict or analyze the consequences of streams from a social, economical, or environmental perspective. And last but not least, we have explainable AI. The idea is that when developing these models for string event detection and impact assessment, we need to the users to trust in the model's strength, in the models learned. So the objective with explainability is to provide experts with more or less comprehensive representations of what the model has learned, of what are the most important features when an output, a detection or an impact assessment output is provided by the model. As I said, this step is crucial. This explainable AI is crucial for the deployment in real scenarios of these models. So based on the detection, impact assessment, and explainable AI tasks, what we present, or what we introduce, is the AIDE Toolbox. And the AIDE Toolbox is a generic framework to simplify complex machine learning workflows, first for the detection and characterization of spatiotemporal string events, and then for the impact assessment of string events on environment, society, and economy. This toolbox has been developed by using the Python programming language. We have been using the well-known PyTorch library for deep learning, and also the PyTorch Lightning interface built on top of PyTorch in order to simplify the code implementation. And the toolbox follows a three-stage pipeline, which is the one we have here. First of all, we have a first stage about the dataset generation. We have, or the toolbox is capable of developing customized scenarios defined by implementing different dataset classes. Now I will give you some more details on how to implement. These dataset classes have to follow the Python dataset class format. It's capable also of covering different string event types, floods, storms, heat waves, droughts, given provided that we have the data in order to perform these case studies, we can cover these string event types. And it supports different data dimensionality, one-dimensional, point-wise or time series, two-dimensional, spatial, and three-dimensional spatial-temporal. The second stage of the toolbox is the architectural specifications and implementation. We have covered, based on several packages in the literature, a wide range of machine learning, outlier detection, deep learning algorithms. And the toolbox also supports user-defined models and loss functions in case we are not interested in those covered by these packages in the state-of-the-art. So the toolbox is also capable of loading models implemented or loss functions implemented by the users as well. Finally, the last stage of the toolbox is the evaluation and analysis of results. We have multiple evaluation and visualization options, and we have a characterization and an explainable AI module. Let me describe with more detail all these different phases of the pipeline of the AIDE Toolbox. This is the whole scheme, summarizing all the contents, all the different modules in the toolbox. It's a bit complex, so I'm going to try to go step by step in order to facilitate the description. And the first part of the scheme or the AIDE Toolbox we are going to review are the user-defined or most of the user-defined modules in the toolbox, which correspond to the data loading, the dataset generation, and also the specifications of the architecture, implementation, and evaluation. All these parameters we need to define in order to deal with the data, the architecture, and the evaluation stages of the pipeline. If we go to the user-defined modules, we have said that AIDE is a modular tool. As I said, it enables users to define new models, metrics, and losses, to accommodate different data modalities, and to adjust systems specifications. Regarding the system specifications, the first thing we need to do, apart from having a database in order to address a particular task, imagine heat wave detection, is to set or to prepare a quite user-friendly configuration file. We have a template. We are providing a template for the configuration file in the GitHub repository at which the toolbox is available. This is the link, indeed. It's here on the right side corner. And given this configuration file, one of the things we need to define in the configuration file is the task type, the type of the task we are going to perform, if it's detection or impact assessment. And then we need to provide parameter values for the four functionalities the toolbox implies. The data description and dimensions, point-wise, spatial, temporal, the architecture selection and definition. Then we'll see through the tutorial an example of the configuration file. The implementation, parameters regarding the toolbox initialization and core parameters, and finally the evaluation, parameters regarding metrics, visualization, characterization, and explainable AI. When coming to the data loading and pre-processing, we need to define a PyTorch dataset class following the PyTorch guidelines or in order to load the database we have for this task. Imagine again a heat wave detection. Within this class is defined by the user, so the user can modify or can prepare the implementation of the class as they wish, but it's recommended to perform some data pre-processing, some standard cleaning as usual, and some, even given that we are dealing with the string event detection or impact assessment task, specific transformations related to anomaly analysis, such as removing the trend or the seasonality of the data in order to highlight those anomalies before being introduced as input to the architecture. It's important also that the dataset class format data observations. What is required by the architectures developed by the toolbox is to have a dataset class which is providing at every iteration of the training procedure during the training stage of the architecture, both input features and ground truth labels. Input features which will be processed by the architecture, the machine learning architecture selected, and ground truth labels we are going to use both for training purposes in order to learn from them during the training phase, and also for evaluation purposes once the model has been trained. And also the dataset class provided by the user, it has to partition the data into training, validation, and test splits. That's also important in order to follow the strategy of the pipeline when dealing with the data, when solving each application. Once we have prepared the data, we can go to the next stage of the system, which is the one related to the architecture implementation and specifications. It's still in the middle between user-defined and toolbox. Most of the functionalities are provided by the toolbox, but still, as we mentioned before, the toolbox also allows defining user-defined models and user-defined loss functions in case we are not interested in the ones which are integrated thanks to the packages available as backends in the AIDE Toolbox. Now we are going to review these packages. That's in the next slide. As I said, for the model training and validation, the toolbox covers machine learning models from the most classical approaches to the most novel deep learning architectures. To this end, we have selected, or we have chosen 4 widely recognized and highly active libraries in the literature, in the state of the art. The first one is Python outlier detection, which is about classical detection algorithms. Then we have segmentation models PyTorch in order to for the development of encoder decoders for spatial segmentation in case we would like to model spatial dependencies for the detection task or for the impact assessment one. Then we have the third backend or package available in the library, which is integrated in the AIDE Toolbox as well, which is deep learning for time series and sequences in order to model temporal dependencies. Here we have architectures such as LSTMs, GRUs, time series transformers, etc. And finally, we have GPyTorch, which is a package which allows for advanced probabilistic regression using Gaussian processes. This is implemented mainly for impact assessment, but it could be also slightly adapted to the case of detection, if necessary. More things regarding the packages. The advantage when integrating all these packages available in the literature is that they are continuously being updated. And if they incorporate new methods proposed by authors recently, given that the toolbox is generic, we are able to directly integrate these methods in the toolbox for using them for detection and impact assessment purposes. And then another advantage or another possibility capacity the toolbox has is that it has or it provides TensorBoard compatibility. TensorBoard is an interface in order to show the real-time insights about the model performance during training. During training, we are interested about the loss value for the training and validation subsets in order to see if the model is converging well, in order to see or to measure stability. And also we could be interested about the values of other scores for providing or for seeing the performance of the architecture, such as the F1 score or the accuracy. All these metrics, all these loss values can be monitored thanks to a TensorBoard interface. Then we'll see how it works in the AIDE Toolbox. It has been implemented or it has been integrated to this end. More aspects we should review only before continuing to the next stage. Here we have also highlighted in the table on the right side, we have some examples of models which have been integrated in the AIDE Toolbox thanks to these packages in the literature: kernel density estimation, PCA, k-nearest neighbors. We have also multi-layer perception, LSTMs, even very, very recent approaches in the literature, such as this mixture vision transformer or graph-based models such as Lunar. All of them, given that they are provided by these backends we have integrated, by these packages we have integrated in the AIDE Toolbox, they can be used for addressing a particular task. And this is also very, very helpful for benchmarking, because given the same task, given hit with detection, given a particular database, a set of input features, a set of ground truth labels, we are able to compare the performance provided by different approaches by using the toolbox, simply by changing the name of the architecture we are going to implement in each of our experiments. Let's go to the third stage of the pipeline, which is about evaluation, metrics, visualization, characterization, and explainability. Now I'm going to describe a little bit more in detail these aspects. First of all, let me recap about the stages we have been following so far. First, data loading, then model implementation. Once the model has been implemented, we train the model, and once the model has been optimized, remember that we had a test subset for testing and inference. Based on this test subset, we have defined, or we have partitioned in the dataset class, allowing to read our data for a particular application. We are able to compute a set of evaluation metrics. We have integrated two well-known packages in the literature to this end, scikit-learn and torch metrics, and they cover most of the well-known metrics necessary or required in order to assess the performance of detection models, such as mean square error, correlation, accuracy, precision recall, well-known ones. Moreover, thanks to the visualization of results, AIDE Toolbox is also capable of providing visualizations. These are going to be stored in an easy-to-read text format, in the case of characterization, and also in the standard image files. And thanks to the support of the matplotlib library, and also some extensions or some additional libraries which provide distribution and scatter plots, the Seaborn package, or geolocated spatial detection maps, thanks to Cartopy. Also, the toolbox provides a temporal plot to summarize detection signals over time, and confusion matrices. With all these figures, with all these visualizations, we are able, besides the evaluation metrics, to analyze the results provided by the toolbox for a particular detection or impact assessment task. Let me talk a little bit also about the characterization module in the toolbox. It's a module we have implemented for the detection task, and it constitutes a post-processing stage to anomaly detection. Here on the right side of the figure, we have an example of drug detection through time, different spatial maps. And what we see is that the toolbox, or what the toolbox is going to provide, is continuous probabilities generated at this output. Given these continuous probabilities, probably for the analysis of events, we are more interested in highlighting blobs or event blobs, regions at which the event has happened. And when aggregating these continuous probabilities into event blobs, probably this may be unclear or less informative than the continuous probabilities. So somehow we need to summarize also the information covered by the regions highlighted based on these continuous probabilistic maps. In order to characterize or to summarize the characteristics of the aggregated locations a priority, we will do something similar to this figure we have here on the bottom. Based on the continuous probabilities, we will highlight by means of a threshold those locations which are which constitute locations affected by the strings, whose probability is higher. In order to summarize the characteristics of these aggregated locations with the objective of tracking anomalous behaviors in these large dynamic data streams more effectively, we are going to follow these steps we have here below. First, the thresholding. As I said, it can be predefined. We can set the threshold we are interested in. These are probabilistic values, so it will be a threshold between 0 and 1, or it could be validated based on the validation subset provided by the dataset class, one of the partitions, the second partition we defined for dealing with the data. This threshold is going to highlight locations of the specific event, the specific hit weight we are studying, for instance. Once we have highlighted these regions, the next stage is to perform clustering and morphological processing. This is optional, but we provide the user the possibility of defining some parameters in order to group locations into regions, depending on their distance, in order to consider them all together for the characterization, for the computation of properties. And also, we give also the user the possibility of removing locations not meeting conditions for an anomaly or a string event. Once we have properly defined all these regions, the final step is to compute the analytics, and we are going to compute properties such as the extent in terms of number of pixels or number of time steps affected by the stream, the centroids, which inform about the location at which the streams are happening, and also probabilistic descriptors such as the maximum, minimum, mean, and standard deviation values of the probabilities in order to inform about the severity or the intensity of the events through time at a specific location. All then together provide this characterization of the event. Finally, We have also an explainable AI module for model understanding. The module is built based on the Captain library, also for PyTorch. It's a Python library which provides feature attribution methods. And the objective of these feature attribution methods is to interpret how the model works. Here we have an example. Based on this drought detection we have performed in Russia in 2010, we are not only interested in detecting the event, in highlighting the moment the event is happening, but also we are interested in knowing why the event has been highlighted, why the event has been detected based on the input features to the model. So we are not interested only on the output of the model, but also on which features at the input of the model has been more relevant in order to perform the detection. In this case, we have provided, in order to perform the drought detection task, we have provided the model with up to 8 different features: features regarding surface and root moisture, features regarding vegetation health, gross primary productivity, vapor tip, and leaf area index, and also earth temperature, humidity, evaporation, and transpiration. By using explainable AI, by using explainable feature attribution methods, we are able, at the moment the drought is happening, of looking at the features which have been more relevant in order to highlight this drought. In this case, when the drought is happening, when the system has been able to identify the drought, air temperature, 2 meters, evaporation, vapor tip, and leaf area index, according to this magnitude of the attributions, have been the most relevant features in order to identify this event. So the objective is to determine the relevance of inputs for a specific prediction, and this could have several purposes. For instance, intermodel comparison. If we have 2-3 different models, in order to see if the models behave similarly and they take into account the same features for providing the detection, or they are considering different ones. It's something it could change depending on the architecture. Also, in order to identify inconsistent results or for debugging purposes, it's a way of determining or identifying if our system is working as expected, or it's highlighting the features which in principle should be more descriptive of the event we are modeling. And in case it's not doing this job, we can think about ways, depending on the performance we get at the output, ways of improving the performance of the architecture, and also to discover dependencies between features. For the aggregation, in the AIDE Toolbox, based on Captain, we are going to provide explainable AI outputs or attribution outputs for every sample over specific dimensions. We can select the dimensions to which we are going to attribute. And also, in order to perform attribution, we should highlight a region of interest at the output of the system to which we would like to attribute. And in order to highlight this region, the AIDE Toolbox allows for providing or to selecting masks to highlight those regions. And this mask could be based on low error outputs. For those outputs, the model is performing very, very well. For those outputs, the error of the model is very low. Or it could be based, this mask, on a specific ground truth classes. If we have, for example, a categorical storm detection, and we have several categories for storms, we could attribute with respect to one of the classes of storms we have. We could have also a mask, or we can have also a mask based on high score predictions. We can assume that the high score predictions, those predictions whose probability, corresponding probability is very, very high, we can assume this then as anomalous events and attribute with respect to them. Or even the user, based on the dataset class, could provide a specific mask, custom mask, in order to select the region they are interested in for attribution purposes. In order to finish, here we have also a summary of the metrics, visualization, explainable AI techniques covered by the toolbox, thanks to all these libraries, Python libraries. For the case of explainable AI, for instance, we have the well-known salience, integrated gradients, also Shapley values, which are very, very common, etc. We have also this summary on the table. And now we have seen the whole pipeline with a little bit more detail as at the beginning. The next stage of the presentation, I would like to show you a little bit in action the toolbox. I would like to show you the performance of the toolbox. Let me change, please, the screen I'm sharing so I can show you the tutorial. It's a tutorial about drug detection in Russia using a 3 convolutional encoder-decoder network, which is user-defined. It's not part of the backends. It's not part of the packages we are considering for which are integrated in the toolbox. It's a user-defined model. Now I will show you some code or some scripts for illustration purposes. So let me change the screen I'm sharing. Just a second. So we can go to the tutorial. Okay, can you see the screen with the tutorial?
Yes.
Okay, perfect. Thank you. Thank you, Manon. So it's a tutorial for illustration purposes. What we have done is to prepare a Python, a Jupyter notebook in Python, so it's easy to show the results step by step. But I would like first to introduce a little bit more the material we have. This is the public repository of the toolbox, the AIDE Toolbox. It's already public. Here we have some description of the toolbox and some easy instructions in order to start using the toolbox. First, we need to create an environment and to start to install all the dependencies of the libraries which are required in order to use the toolbox. And then we have here, this is a tutorial different from the one I'm going to show you. This is already available in the GitHub repository. The one I'm going to show today will be hopefully available also in the following days. We have some lines of code we could directly use in a terminal, via terminal, in order to use the toolbox. It's pretty easy once we have defined the configuration file to run the toolbox. We have also the link to read the docs with all the documentation available in order to know with more details the meaning and the behavior of the different functionalities involved by the toolbox. We have here the template of the configuration file and some instructions, a quick overview, the API reference, etc. We'll be updating. Still, we are working. This is the first final version of the toolbox, publicly available, but of course, we are open to modifications. We are open to improvements, and we try also to complete the material as much as possible in order to simplify the users when dealing with the toolbox, in order to make it simple, this procedure. Coming back to the tutorial, once we have seen all the material we have, what I have simply do is to open the Jupyter notebook. And I wanted to mention that the steps we are going to follow here, although they seem more complex, these are the ones followed by the main script of the toolbox. The main script of the toolbox, I think I have it open here. It's not here, sorry, I cannot see the tabs here. And if you see, it's very simple. The first script or the main script of the toolbox is pretty simple, only a few lines. They correspond to the different stages we have been reviewing through the presentation: data loading, model implementation, model training, and finally test and inference stages. These are the stages we are going to review now in the notebook, following this use case of drug detection in Russia. I have already executed the notebook in order not to lose a lot of time during training, and so I can show you all the results, but I'm going to go step by step, cell by cell, in order to illustrate the procedure we should follow, we will follow in order to make use of the toolbox, in order to solve or in order to address not only this example use case, but other use cases, other string event detection tasks we could be interested in. The tutorial or the notebook has some information. I'm going to try to summarize during the presentation, not to have to read them together. It has the links to read the docs, to everything, to all the material I was mentioning before. First of all, we are going to see the prerequisites of the toolbox. Then we'll introduce the database for this use case. The model we are going to use, a 3D CNN, and its training stage, evaluation stage, and visualization of results. First, the notebook, what it's doing is to see that we are in the proper folder in order to start working with the toolbox. I can show you also the route to the folder or the contents. Let me go back. I was doing some tests before. This is the main folder of the toolbox, and we have several subfolders with all the scripts involved in the procedure. Here we have the main script, and these are the folder, or this is the folder we should be in order to start playing with the toolbox for a specific use case. Here we are in the folder we should be. Then here we have some lines of code for installing dependencies. These are not required because we have already set the environment and we have followed the instructions we had in the GitHub repository. All these lines, this is what it should be done first. Even I would recommend you also trying out with the tutorial. It's already available in order to verify the toolbox is working properly. And once you see the toolbox is working properly with this tutorial or with this use case we provide as example, in principle, you should be ready in order to start playing with other use cases by using your own databases. Here we are also loading all the required libraries. The reason we are loading the libraries here is because we are going to make use of some of them for visualization purposes, and they are required here, but it's not necessary to load all these libraries every time you need to use the toolbox. In principle, by calling the toolbox only with this line, this is for a particular experiment using k-nearest neighbors. This is for an experiment using an LSTM for modeling temporal dependencies. Only with this one line and configuring or setting properly the configuration file. Now we'll review. In principle, it should be enough in order to run the toolbox. But here, in order for illustration purposes in the notebook, we had to load again the required libraries. We come to the configuration file. This is the first stage of the procedure. We are reading the configuration file and we are showing all the information of the configuration file through the screen. What I'm going to do, because I think it's going to be easier, because here when being printed, the information in the notebook is sorted alphabetically. So what I'm going to do is to show you the configuration, the real configuration file here, so we can review all the parameters we should configure together. First, we have a header with the name of the toolbox, the type of the task we are going to perform, classification, outlier detection, or impact assessment. If it's going to use, if we are going to train from scratch the model, or we are going to load an existing model. In this case, we are using already an experiment we already did some weeks ago, so we are not training from scratch. What we are doing is to load the stored weights from a previous experiment we did. The path that we would like to, at which we would like to save the results from the experiment. Here we have a debug option. It consists in limiting the number of samples we are going to use through the different stages of the toolbox in order to verify the toolbox or the whole chain, the whole pipeline is working properly. This is helpful because these are very, very time-consuming experiments. So I think it's a good practice to limit the number of samples in order to ensure the whole pipeline is correctly executed. And then once we have verified, once we have debugged the code, we are ready to run the whole experiment. And then we have parameters regarding the data set. This is depending on the database we are defining, given that the data set is defined by the user by using a PyTorch class. We are going to have different parameters depending on the dataset class we have defined. For this use case in Russia, drug detection in Russia, we need to provide the routes to the files containing the input variables, which are provided by the System Data Cube, the ground truth labels from the geocode disaster database. We are also highlighting, or we are also selecting the locations for training, validation, and test subsets, latitude and longitude coordinates, the batch size for the corresponding training, validation, and test subsets, the input features we have selected. We are going to take into account 3 input features for this simple example of drop detection. We are taking into account surface moisture, air temperature 2 meters, and evaporation. Some acronyms, we are selecting all these features. In case we're interested in pre-processing the data by computing the climatology, these are the routes at which to store the climatology files, not need to recompute them again every time we do a new experiment, if we are interested in trying out several models. some options regarding pre-processing, the temporal slices we are going to use for training, validation, and test purposes. In this case, what we are doing is to select for training and validation purposes the same time interval between 2003 and 2010. But by considering different locations for training and validation in order to make the validation properly. And then for test purposes, we are selecting a different time interval between 2009 and 2012, and also at a different location from the ones considering in training and validation. Batch size, number of classes. In this case, we are performing drought detection task as a binary classification task by distinguishing between drought and non-drought conditions. So a number of classes is equal to 2. And then we have some parameters regarding the architecture definition. We have that the architecture, as I said, is going to be user-defined. So it's set to true. The time of the architecture we are going to use, which is 3D CNN. This is the name of the class implementing the architecture. Given that it's a user-defined model, it needs to correspond with this model. And also the input and output model dimensions, which are 3 dimensions, space and time, 3-dimensional ones. I can show you also where the architecture is stored. It's in the user-defined folder, followed by models. Here we have a user models script. In principle, it should be here. Here we have some user-defined architectures. This is the one we are going to use now. If you are interested, please let me know afterwards. I prefer not to, because if not, I'm going to spend a lot of time by reviewing. But even if you have the opportunity of dealing with the toolbox after the presentation, don't hesitate to contact us in case you have doubts with all the implementation. The database I mentioned before is in the databases folder. This is the script the user should have prepared in order to solve this particular task. And once we have, let me finish with the configuration file. In the configuration file, finally, we have also parameters regarding the implementation of the architecture. The loss function, in this case, we are going to take into account, or we are going to use for training purposes, a sigmoid focal loss with some parameters. We can define also here in the configuration. The optimizer, which is going to be the well-known add-on. The trainer, we are going to make use of GPUs, 500 epochs. We can also define early stopping in order to stop the training procedure if we see that the validation loss starts increasing, the validation loss or a specific metric in the validation set. We can select the metric we are interested for monitoring the training stage. More important things. Finally, the parameters regarding the evaluation of the model. Parameters regarding the metrics we are going to compute for quantitatively evaluating the results, the area under the curve, the average precision, F1 score, accuracy. We can select the ones we are interested in. For the visualization, some parameters, characterization parameters, and finally, explainability. In this case, we have selected as attribution method integrated gradients. We choose second, third, and fourth dimension, space and time dimensions, as the ones to be aggregated for explainable purposes. And we are not using a mask in this case because it's a small region. It's centered around the region of interest for interpreting the event, but we could be selecting also a particular mask if we are interested in highlighting a particular region for explainability purposes. Once we have defined the configuration file, we have it here printed. We go to the database. We have been reviewing also based on the parameters in the configuration file. We have some instructions about the methods the dataset class in PyTorch should contain in order to be readable by the toolbox. We go to the dataset and data loaders in order to read the data through the different iterations involved in the training procedure through the different epochs in the training. We are going to visualize the data only to have an idea that the data is correctly there. We have been able to properly load the data in order to be used by the model. Here we have some auxiliary lines of code for visualization purposes, and we are visualizing a train batch, a validation batch, and a test batch. Here we have the train sample. The batch size was 32 time steps. In this case, in order not to show the 32 time steps, which will be very, very long or very high number of columns, what we have done is to represent for at every row a variable. We have surface moisture, temperature 2 meters, and evaporation, the three first rows. And then the final row is the drought label, the drought ground truth. We have 1 out of 10 maps for the different input features in order to visualize the contents of this batch. We see that in this case, we don't have a drought happening in this time interval, not for the training sample, but if we go to a validation sample, we see that here we have a binary mask highlighting in yellow those locations corresponding to areas affected by the drought. Again, the series of the different essential climate variables, also for the test sample. We are visualizing on only one example in order to get an idea that the model, that the data has been properly loaded into the AIDE framework. Once we have reviewed the data, we come to the model and training stage. And here we start with the different steps we are following in the, if you remember from the main script, we were following here. We define the backbone for the model to be trained. We load the data, first step. We implement the model, second step. We also plot the model in order to see the corresponding layers. They have been loaded properly. We have 3 convolutional layers. They are not sorted according to the definition, not in this printed version or this summary, but if you go to the definition of the architecture, you will see that how they are sorted. We have convolutional layers followed by batch normalization layers. We have dropout. I think it's deactivated because of the probability, but this can be tuned, even it's a user-defined module, it should be easy. We have leaky ReLU activation functions right after the convolutions. We have max pooling layers in between convolutions in order to decrease the dimensionality of the data for encoding purposes in order to perform the detection by following an encoder-decoder architecture. Once we have implemented the model, we come to the training stage. And in the training stage, we see also here the TensorBoat extension for monitoring the different metrics. The model has been already trained, so we can see some statistics or some metrics. I'm not going to execute the training stage now, but thanks to the interface, during the training process, we are capable of monitoring how the training and validation losses evolve through the different epochs, how the F1 score, which is the metric we are using as a stopping criteria, it's evolving not for the training, because in principle, we can show also for the training the F1 score, but we are interested in the validation F1 score in order to store the best model, the one which is providing the highest F1 score. We can monitor the values of all these metrics through the training stage in order to ensure that the training is performing as expected. This will be the interface of TensorBoat integrated in the framework, in the AIDE framework. Once we have trained the model and we have monitored the metrics through the training stage, we come to the evaluation and visualization of results. Based on these metrics, we have selected in the configuration file, and based on the test subset, we are going to evaluate the performance of the model quantitatively, area under the curve, accuracy, average precision. All these metrics are provided by the toolbox only by calling this backbone or classifier.test line of code. And then we come to the visualization, characterization, and explainability of results. What we have done here in this Python Jupyter notebook is to activate the corresponding states and deactivate the remaining ones to show the different visualizations step by step. But this is something which could be done directly all at the same time without waiting or without stopping in the different stages, because all the results are stored in the results folder. I can show you here the results folder. If we go to the experiments, we have this folder. We have a folder for characterization results, a folder for the checkpoints for the different models stored, the different weights up to the, we are storing the 5 best models, the 5 according to the F1 score metric for validation, the logs for the TensorBoat, which can be visualized through the interface I have just shown, the spatial visualization maps for the different time steps, the explainable AI results. All of them, they are stored in PNG format, is a well-known one, the temporal evolution. All the results are stored here, so it's not necessary to go step by step, but this is something we are doing here in the notebook for illustration purposes. We do the inference. Thanks to the inference, we are able to get the confusion matrix for the experiment. Then we also get the temporal evolution of the detection through time. This is an aggregation based on the spatial maps, based on the continuous probabilities. And for the region the drought is happening, we can see how the drought has been detected through time in Russia. We have performed also here characterization, also by calling the inference. Even we could select a different principle. By default is the test subset, that if we are interested in performing these visualizations for the training or validation set, in principle it should be possible. Also in order to get an idea about how the model has learned from the data. Here we are plotting an example spatial detection map. Some results about the characterization, the extension in terms of number of samples, the location, the coordinates at which the drought event is happening, the weighted coordinates depending on the probabilities of having the drought, and also the minimum, mean, maximum, and standard deviation probability. Finally, we perform the explainable AI step, also over the test subset, and here we are plotting the attributions provided by integrated gradients for a particular time step. And we see that for this particular time step, the air temperature 2 meters, in order to provide the prediction, has been the most important feature, followed by surface moisture and evaporation. We see also the attributions for the drought and non-drought classes. We can measure them then in terms of magnitude, or how we would like to perform the corresponding analysis. So this will be the end of the complete pipeline of all the functionalities that the toolbox provide. I'm going to finish, because I think I'm running a little bit out of time. I'm going to finish with the presentation, and then if you have doubts, please feel free to ask me. Let me share again the presentation to finish with. I wanted also to show you this benchmark we have been able of establishing by considering different algorithms integrated in the toolbox. It's one of the advantages of the toolbox, given that it's very, very easy. Once we have defined a particular use case based on the database, it's pretty easy to change the algorithm we would like to assess its performance. We can assess the performance of multiple algorithms in order to compare them, in order to select the most optimal one. So here we have assessed the performance not only of the 3 convolutional architecture I have just shown with the notebook in Python, but also of all these algorithms, pointwise algorithms provided by the Python outlier detection library, PCA, kernel density estimation, spatial algorithms, segmentation models, PyTorch, UNet, LinkNet, temporal algorithms, time series AI package. We have the well-known LSTM, GRU, time series transformer, and also as an additional user-defined model, spatio-temporal, we have also provided results for the convolutional LSTM. So we are able to compare the performance of different approaches by following the same scheme defined by the AIDE framework. To finish with the presentation, these are the take-home messages. First of all, AIDE, it's an open source system for the quick and easy deployment of data-driven algorithms for the detection, characterization, and impact assessment of anomalies and strings in spatio-temporal data. It constitutes a novel benchmarking suite that will help bridge the gap between earth scientists and machine learning experts by providing a framework that is easy to use by the former, by earth scientists, while remaining customizable for the latter, for machine learning experts, in case we would like to do, or we want to change, or we want to try out different configurations. AIDE provides us this flexibility. AIDE also provides results using diverse metrics and visualization approaches, which enables a comprehensive evaluation of the method performance. And finally, the AIDE Toolbox can be highly beneficial in remote sensing and geosciences, facilitating efficient monitoring and understanding of anomalies and extreme events. So this is the end of the presentation. These are the related references. We had just got the paper accepted to be published in the Geoscience and Remote Sensing magazine with all the information I have tried to cover during this presentation today. Maybe a little bit more detail, but all the figures, all the results we have seen during the presentation, hopefully it will be published very, very soon. And also all the related references regarding the contents of the presentation. I would like also to finish the presentation acknowledging the XAIDA project. this toolbox was developed as part of participation of University of Valencia of the image signal processing group in the XAIDA project. So it was developed thanks to our participation in this project in XAIDA. And that's the end. Now that's the end of the presentation. Thank you so much for your attention, for being in the webinar. And if you have thoughts or questions or something to discuss, please, I will be very, very happy to discuss now with you. Thank you.
Thank you, Miguel-Angel. So I think we have some minutes for a couple of short questions. So please unmute yourselves or use the chat as you feel more comfortable to address some questions to the speaker.
Thank you, Amir. I read you. I was able to open the chat. So if you want to write in the chat, I can also see you. Maybe 40-45 minutes in order to do a presentation of a toolbox is not enough. Maybe it would be nice to organize kind of a workshop or maybe a longer tutorial in order to provide more details, or even in order to know your interests in terms of the applications you would like to address about detection and impact assessment. If there is interest, please feel free to contact us, or even if you are trying out, or if you are installing the toolbox, trying to work with it, feel free to contact us, and we can provide you with support if you need it.
Hello.
Hello, Amir.
Can you hear me?
Yeah, I can hear you.
Yeah, thank you for such wonderful presentation. I was following this project sometime, and also I read some about the toolbox as well. But unfortunately, today I joined very late because I had some issue with my bicycle. So I want to ask that I'm also starting my have started my PhD here at University of Twente in Netherlands.
Great.
So and I'm doing the research in the context of analyzing the extreme and compounding events under changing climate in Pakistan. So I'm also interested to utilize this tool in my research as well. So hopefully I will follow these links and which you just mentioned in the slides as well. So and I will come up with you if I find any difficulty here.
Sure. Even if you had doubts or there's some information which is not available there, and it could be useful for you to use the toolbox, send us an email to whoever of the authors.
Okay.
Send us an email, and we'll contact to you, and we'll support. Yeah, it's true that the toolbox has been recently published, and it's true that although we have been testing the toolbox by following 2-3 different case studies and also different data modalities in order to try to ensure that everything works well. But I think it's a very, very crucial and very important stage if there is interest in the community, if you are interested in using in the end the toolbox to provide us with feedback for improvement. Even that at the point, if you are developing a particular case study and you feel I missed this option, or I think it will be very, very helpful, these are the things we could try to take into account for improving the toolbox. Our objective, if there is interest in the community, is to continue growing the toolbox in order to incorporate all the feedback we receive.
Yeah, sure. Because you just mentioned about the drought in Russia 2010, and at the same time after we had the floodings in Pakistan 2010. So these are the extreme, like the extreme event that we have in the context of extreme rainfall. But on the other hand, there was extreme events on like in Russia of heat and drought. So I also have the context that like these extreme, they have the temporal overlaps, either the temporal gap between each other. Like in 2022 we had a heat wave in May, and the next month of June we had extreme temporal rainfall events. So I will study this tool as well, and then I will come up with you. So thank you very much for your presentation and for sharing these wonderful and innovative tools.
Perfect. Thank you so much also for your interest, and hope you find helpful the toolbox with the data you have and the case study. Let us know if you
Yeah,
had
sure.
doubts or whatever, and we are in touch. Thank you.
Yeah, sure. Thank you very much. Thank you. Bye.
I'm reading also in the chat, the event in 2022 in French. Of course, if you have, what is very, very important in order to work with the toolbox is to have a proper database. If there is climate variables available, in principle, there is information which is more or less easily accessible in order to be downloaded. In the case of streams, what is also crucial is the definition of the labels of the ground truth. But having a clear idea about the moment and locations the streams are happening, in principle, the toolbox with this information, it should work well, and it should be capable of providing results or performances for different approaches at the same time in order to get a whole context and to make decisions about the which is the most suitable architecture. About organizing a workshop, if we see there is interest, it's something we could try to foster. Yeah, of course. At the moment, I think this with this presentation, but maybe if you are more interested, maybe in seeing the potential of the toolbox for particular case studies, it's something we could try to organize. Yeah. We should see the proper date, but please let us know also via GitHub or via email, or please show your interest, and if we see there is real interest in these activities, we'll organize them. Great.
Okay, so if there are no more questions, maybe we can wrap this session. Perfect. So thank you very much to the speaker for this interesting talk, and to all of you for attending. And we hope to see you in the next seminar, which will take place 29th of April.
Thank you, Maria.
Soon.
See you. Have a good week.